In the dark ocean of the cosmos, everything drifts, yet nothing is truly lost. Galaxies move like slow-burning embers scattered across eternity, their light stretched and thinned by the long breath of time. Between them lies an infinite stillness, a silence so vast it seems impossible that anything could stay bound at all. And yet across this great expanse, a quiet order persists. Stars remain tethered in spirals, planets cling to suns, atoms hold their trembling cores. Somewhere within the darkness, something unseen is at work, an invisible tension that keeps existence from coming undone. Physicists call it gravity, but the name is only a whisper of what it means. It is not just a pull between masses, but a language of the universe itself, the curvature of space, the shape of time, the memory of creation folding back upon itself. It reaches from the smallest grain of dust to the farthest cluster of galaxies, binding all in a web of unseen geometry. And yet, even this cosmic glue seems fragile. The universe expands, the distances between galaxies widen, and the light that once touched them fades into red and silence. By every measure, it should all have fallen apart long ago. Still it holds. Still, across billions of years, the delicate equilibrium endures, a balance between collapse and escape, between force and void. Somewhere in that balance lies a mystery deeper than gravity, deeper than light itself. Something that should not be, yet is, the quiet persistence of being held. It is here, in the tension between nothingness and order, that the story of the universe begins. In a quiet orchard beneath a pale English sky, a single apple falls. It lands with the simplest of sounds, yet that sound will echo across centuries. To Isaac Newton, it was not the apple that mattered, but the space it fell through. Something unseen had reached across the emptiness, tugging at it. In that invisible reach, Newton glimpsed the first thread of a cosmic web. He would name it gravity, a universal force, binding every object to every other, from the smallest pebble to the farthest moon. It was, he wrote, the same hand that held the planets in their courses, the same pull that shaped the heavens. In a time when the universe was thought to be clockwork and divine, Newton's law of universal gravitation gave it form and predictability. But Newton never claimed to understand how gravity worked. He saw its effects, but not its cause. That gravity should be innate, inherent, and essential to matter, he admitted, is to me so great an absurdity that I believe no man can fall into it. To him, the mechanism behind gravity, how one object could influence another across a void, was a mystery, an unseen whisper passing between worlds. For 2 centuries, his equations held dominion. They guided ships across oceans, charted the orbits of comets, and carried humankind's gaze to the outer planets. Gravity became the architect of motion, the script by which all celestial bodies played their parts. Yet as instruments sharpened, small irregularities began to appear. The orbit of Mercury, closest to the Sun, did not behave as Newton predicted. Its path wobbled. A minute but undeniable precession that could not be explained by the gravitational influence of nearby planets. Astronomers searched for an answer, even imagining a hidden world, Vulcan, orbiting unseen between Mercury and the Sun. But no such world was ever found. Something else was shaping space itself. Then, in the early 20th century, a quiet clerk working in the Swiss patent office began to question the foundations on which Newton's universe rested. Albert Einstein saw not a universe of forces, but a universe of geometry. Gravity, he proposed, was not an invisible hand pulling from afar. It was the shape of space itself, a curvature woven by mass and energy. He imagined light bending as it passed near stars, not because it was tugged by a force, but because space itself was bent by the star's presence. He described time slowing near massive bodies, clocks ticking differently depending on how deep they sat in gravity's well. The cosmos, in his view, was not a static framework, but a living fabric, flexible, dynamic, and endlessly self-referential. In 1919, during a total solar eclipse, this vision was put to the test. Astronomers, led by Arthur Eddington, observed starlight curving around the dark edge of the moon's shadowed sun. The light had bent exactly as Einstein's equations predicted. The newspapers declared, "Newtonian ideas overthrown," The universe was no longer a clock. It was a poem written in curvature. Einstein's general theory of relativity reshaped reality itself. It explained the precession of Mercury, predicted the existence of black holes, and showed that even the passage of time could be altered by gravity's pull. Space and time were no longer separate. They were one continuous entity, space-time, and mass was the brush that painted its contours. But even Einstein's masterpiece carried an unease. His equations implied that the universe could not be static. It must be expanding or contracting. To preserve a steady cosmos, he added a mathematical fix, the cosmological constant, a term that acted as a kind of anti-gravity, holding everything in balance. Decades later, when Edwin Hubble discovered that galaxies were, in fact, drifting apart, Einstein would call that constant his greatest blunder. Yet history would prove that blunder prophetic. For something like that constant, a mysterious repulsive force in the vacuum, would later return under a new name, dark energy. Even as relativity revealed gravity's depth, new questions rose from the void. If space could bend, what gives it that flexibility? What allows the cosmic fabric to stretch, warp, and ripple? What is space-time made of? These were not questions of mathematics, but of reality itself. For relativity was silent on the substance of the vacuum. It described how gravity behaves, not why it exists. In 2015, nearly a century after Einstein's predictions, a faint vibration passed through Earth, stretching space itself by less than the width of an atom. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, had caught the dying breath of two black holes colliding more than 1 billion light-years away. The ripples Einstein had imagined were real. Gravity could sing. It was a sound not of matter, but of space-time itself, ringing like a drum. And yet, in the aftermath of that triumph, the mystery only deepened. Gravity waves carried energy, but through what medium did they travel? Space seemed to behave like a physical fabric, but no experiment could reveal its threads. Physicists began to suspect that space-time itself might be an emergent phenomenon, a byproduct of deeper quantum relationships, where particles are not individual entities, but points of connection in a vast entangled network. In this view, gravity is not a force nor even geometry, but an illusion, the macroscopic echo of microscopic information binding together at the quantum level. The shape of space, in essence, could arise from the invisible dance of quantum entanglement. This idea, the holographic principle, suggests that all the information describing a region of space could be encoded on its boundary, just as a three-dimensional image is stored on a two-dimensional surface. If true, then gravity may not be a fundamental force at all, but a side effect of how information organizes itself at the edge of the universe. The implications are staggering. Everything held together, stars, galaxies, the atoms within every living thing, might be bound not by forces that act across space, but by the logic of information itself. A universe held not by matter, but by meaning. Still, these are whispers of theory, not certainties. The vacuum remains silent about its own substance. Quantum mechanics and general relativity, the twin pillars of modern physics, refuse to meet on common ground. One describes the very large, the other the very small. And between them lies a gulf that no equation yet spans. The story of gravity, from Newton's orchard to LIGO's trembling mirrors, is a story of discovery wrapped in absence. Every revelation unveils a deeper ignorance. Each thread traced leads to another hidden weave. The more the cosmos reveals, the more it conceals. Through it all, the universe continues to hold. Galaxies spin, tides move, light bends and time flows. Each moment is balanced on invisible geometry, a quiet architecture that science has yet to touch. The first threads of gravity were never just mathematical, they were existential. They spoke of a universe unwilling to fall apart, of a fabric that endures despite every tension within it. In that endurance lies the most haunting question of all. Not how gravity holds the universe together, but why the universe insists on being held at all. For most of the 20th century, cosmologists believed they understood the rhythm of the cosmos. The universe had begun in a flash of creation, the Big Bang, and had been expanding ever since. Yet, under the pull of gravity, that expansion was expected to slow, the galaxies gradually yielding to the invisible weight of all that exists. The question was simple. Would the cosmos coast forever, or would it one day collapse back upon itself, ending in a final convergence, a big crunch? But in the late 1990s, the light from ancient stars began to tell a different story. A quiet rebellion was unfolding in the sky. Astronomers studying distant Type Ia supernovae, colossal stellar explosions used as cosmic distance markers, noticed something impossible. These dying stars were fainter than they should have been, farther away than expected. When their data were plotted, the universe's expansion did not show signs of slowing. It was accelerating. In 1998, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, confirmed the result. The universe was not simply expanding, it was speeding up. Galaxies were racing apart with increasing velocity, as if pushed by an unseen hand. This single discovery reshaped modern cosmology. It defied every assumption born from Einstein's general relativity, from Newton's gravity, from centuries of intuition about attraction and collapse. The cosmos, once thought to be governed by the quiet deceleration of gravity, was now a runaway creation, expanding. Faster the emptier it became. Something was overpowering. Gravity's eternal pull. Physicists began to call it dark energy, a name that admitted ignorance as much as it suggested power. It was thought to make up nearly 70% of the universe, yet it had never been seen, measured, or directly detected. Its only evidence was motion, the accelerating separation of everything that exists. For the first time in modern science, the universe itself seemed to resist comprehension. The equations of relativity still worked, but now they hinted at something far stranger. Einstein had once introduced his cosmological constant, a mathematical term meant to keep the universe stable, neither collapsing nor expanding. He later discarded it, calling it his greatest mistake, but now his so-called mistake had returned as prophecy. The cosmological constant could describe exactly this repulsive effect, a vacuum energy pressing space apart. If true, it meant that the very fabric of spacetime carried within it a kind of energy, a pressure intrinsic to emptiness. The void, far from being nothing, was alive with potential. Every cubic centimeter of space contained a whisper of energy strong enough to shape the fate of the cosmos. To many, this revelation was exhilarating. To others, it was profoundly unsettling. For the first time, gravity, the binding principle that had held the universe together since Newton's apple, was not in control. Something in the dark was stronger. Something in the silence was winning. The narrator's tone deepens. The images slow. Galaxies drifting apart. Threads of light stretched thin. The cosmic web itself beginning to fray. As the expansion accelerates, vast regions of space are carried beyond one another's reach. Light itself can no longer cross the widening gaps. The observable universe becomes an island, isolated in a growing ocean of nothingness. Distant galaxies fade, their light redshifted beyond visibility, their voices swallowed by expansion. In this vision, the cosmos is not dying in fire or collapse, but in cold and silence, a gradual unraveling where every connection is lost. And still, the question lingers, what holds anything together at all? If dark energy truly drives this acceleration, its nature must lie in the very structure of the vacuum. Quantum field theory suggests that even empty space seethes with activity, fleeting pairs of particles and antiparticles emerging and vanishing in an instant. The vacuum, at its smallest scales, is not a still void, but a restless sea of fluctuation. Yet when physicists attempt to calculate the energy density of this quantum vacuum, the result is absurd. 120 orders of magnitude greater than what observations reveal. This mismatch, known as the cosmological constant problem, is the most severe discrepancy in all of physics. Somewhere between quantum mechanics and relativity, the truth slips away. Perhaps dark energy is not constant at all. Some models propose it evolves over time, a dynamic field known as quintessence, a ghostly energy that shifts with the age of the universe. Others suggest that Einstein's equations may themselves be incomplete, that gravity behaves differently on cosmic scales than within galaxies or solar systems. But the data remains stubborn. Every measurement, from supernovae to the cosmic microwave background, confirms the same haunting conclusion. The universe is expanding faster and faster. If the trend continues indefinitely, the future is written in dissolution. Over trillions of years, Galaxies will drift so far apart that no new light will ever bridge the distance between them. The night sky will darken, its familiar constellations fading into oblivion. Even within galaxies, the stars will die one by one, leaving only remnants, white dwarfs, neutron stars, and black holes. Eventually, even those will decay, their energy evaporating into the cold sea of expansion. It is called the heat death, the ultimate quiet, where entropy reigns and no structure remains to feel the passing of time. And yet, within this terrifying prospect lies a strange beauty. The same force that threatens to scatter all things also allows them to exist at all. Without the expansion, without the fragile balance between gravity and dark energy, the cosmos might have collapsed long before stars could form, before chemistry, before life. The universe's capacity to hold, to remain stable long enough for consciousness to emerge, depends on that precise, improbable tension between attraction and escape, a cosmic equilibrium so delicate that even a fraction's deviation would render reality impossible. In that balance, perhaps lies the meaning of the question: what holds the universe together when nothing should? It may not be a single force nor a single law, but the interplay between opposites, gravity's embrace and dark energy's release, that gives rise to structure, to existence, to time itself. Some physicists speculate that dark energy could even be a shadow of deeper dimensions, the echo of physics beyond our comprehension. If the universe is part of a grander multiverse, each region might possess its own balance of dark energy, some collapsing instantly, others expanding too fast for stars to ever form. Only in the narrow sliver where the two nearly cancel could matter persist. Could observers like us arise to wonder about it? In that sense, the universe's accelerating expansion may not be an accident, but the price of existence itself. The camera drifts outward now, beyond the Milky Way, past the filaments of the cosmic web, to the edge of the observable universe, where light from the first galaxies still travels toward us, stretched thin but not yet lost. It is there, in the dim glow of ancient fire, that the paradox becomes most visible. A universe that expands while holding together, that stretches while sustaining form, that moves toward emptiness yet remains filled with meaning. The great unraveling of the universe is not a story of destruction, but of tension, the endless conversation between gravity and the void. One binds, one releases. Together, they write the history of everything. In the vast stillness of intergalactic space, light carries memories older than stars themselves. It travels unbroken for billions of years, crossing gulfs of emptiness, whispering of what once was. When it finally reaches human instruments, the great mirrors of orbiting telescopes, the deep-cooled sensors of cosmic explorers, it brings with it a message from the birth of everything. That message is faint, softer than the breath of an atom, but it holds the entire history of the universe. In the early years of the 21st century, the Wilkinson Microwave Anisotropy Probe, WMAP, began to chart that ancient echo, the cosmic microwave background, a ghostly radiation left over from the Big Bang. Decades later, the Planck satellite would refine the image with breathtaking precision. What they found was a cosmic fingerprint, a delicate pattern of light and shadow frozen into the fabric of the sky. This faint glow, spread evenly across the heavens, is not random. It carries the seeds of everything. The first ripples that gravity would one day amplify into stars, galaxies, and clusters. But hidden within its spectrum was a deeper revelation. The universe was not made primarily of the things humans could see. Only a small fraction, 5%, was the ordinary matter of atoms and dust of the tangible world. The rest, an overwhelming majority, was invisible. The numbers stunned physicists. Roughly 27% of the universe's total content appeared to be dark matter, an unseen substance that exerts gravity but emits no light. And about 68% was something stranger still, a form of energy permeating all of space, driving its accelerated expansion. Dark energy. It was not merely invisible, it was unknowable, a property of the vacuum itself, as if emptiness had decided to participate in the story of creation. To understand this hidden majority, scientists began to look for its fingerprints in the behavior of galaxies. The deeper they peered, the more they saw evidence of an unseen architecture. A cosmic scaffolding made not of light, but of gravity's invisible hand. Galaxies did not float randomly in space. They gathered along vast filaments stretching millions of light years, forming colossal clusters where these strands intersected. Between them yawned immense voids, cosmic deserts nearly empty of matter. Computer simulations, the great digital universes crafted inside supercomputers, showed that this web of dark matter dictated everything. It was the invisible foundation upon which the luminous cosmos was built. Every spiral galaxy, every burning star, every planet and atom, all followed the pathways carved by this shadowy structure. The evidence came not from direct sight, but from distortion. When light from a distant galaxy passes near a massive object, gravity bends it, not just the object's light, but the space it travels through. This phenomenon, known as gravitational lensing, became a tool to map the unseen. In the late 1990s and early 2000s, astronomers began measuring subtle warps in the shapes of background galaxies. These distortions, tiny and consistent, revealed the presence of dark matter clumps, invisible clusters bending the light of galaxies billions of light years away. The Hubble Space Telescope and later instruments traced these gravitational echoes, sketching outlines of dark matter where nothing else could be seen. It was as though the universe was made of glass, warped by invisible fingerprints pressed into its surface. Every new image, every distortion, confirmed the same haunting truth. What is most essential in the cosmos cannot be observed directly. But even as dark matter emerged as the great unseen architect, a second mystery grew darker still. While dark matter pulled things together, dark energy pushed them apart. The universe was both binding and unraveling, two opposite forces locked in a cosmic equilibrium. This delicate tension determined everything. If dark energy were slightly weaker, gravity would have halted the expansion, and the universe would have collapsed back into itself, a fiery implosion known as the Big Crunch. If it were stronger, the cosmos would have torn apart long before stars and galaxies ever formed. Instead, it balanced perfectly against the pull of matter, a razor's edge of cosmic probability. To many cosmologists, this fine-tuning seemed impossibly precise. It hinted at something deeper, a mechanism, or perhaps a principle, woven into the laws of physics themselves. What was this invisible energy that filled the vacuum? Was it a property of spacetime, Einstein's cosmological constant reborn, or something entirely new, a dynamic field yet to be discovered? In laboratories on Earth, scientists tried to replicate the conditions of the early universe. Particle accelerators probed the fabric of matter, searching for exotic particles that could explain dark matter's gravitational fingerprints. Theories emerged, weakly interacting massive particles, or WIMPs, axions, ghost-like quantum fields, sterile neutrinos, almost undetectable cousins of the known neutrino species. Yet none revealed themselves. Every experiment ended in silence. The detectors, buried deep underground to shield them from cosmic noise, continued their vigil. Their sensors waited, year after year, for a single particle to collide, a single flash to announce the presence of the unseen. But the universe withheld its secret, and so, cosmology entered a new age, one defined not by what was known, but by the geometry of ignorance itself. The cosmic microwave background became a map not only of ancient light, but of what was missing. Its delicate fluctuations told scientists how much dark matter shaped the early cosmos, how much dark energy now drives its expansion, and how the balance between them has changed over billions of years. Map and Planck showed the universe's shape, flat to within a fraction of a percent, suggesting that space itself extends infinitely, with no edges, no curvature, no end. Yet inside that flatness hides the greatest asymmetry of all, a universe filled mostly with what cannot be seen. It is a quiet paradox. The more precisely humans measure the cosmos, the more they discover how little of it they understand. In the silence between galaxies, this invisible architecture continues its work. Dark matter gathers like mist, binding light and dust into galaxies. Dark energy pushes them apart, stretching the cosmic web wider with every passing billion years. Together, they choreograph a cosmic tension. Creation and dissolution intertwined. What holds them in balance remains one of the most profound questions in science. Some physicists wonder whether dark matter and dark energy are two faces of a deeper reality. perhaps emergent phenomena from the quantum fabric of spacetime itself. Others propose that gravity may not be what it seems, that at vast cosmic scales, its strength shifts, hinting that Einstein's equations might one day require rewriting. But for now, the picture remains suspended between clarity and mystery. The telescopes keep watching. New instruments, the Vera Rubin Observatory, the Euclid mission, the Nancy Grace Roman Space Telescope, are designed to map billions of galaxies, tracing the shape and evolution of the cosmic web with unprecedented detail. Each one aims to answer the same quiet question. What truly governs the universe's fate? Matter, energy, or something deeper still? And so the search continues, guided not by light, but by its absence. It is a pursuit defined by patience and awe, a science that listens to silence, measures shadows, and maps the unseen. For in the faint distortions of ancient light, in the trembling of spacetime itself, lies the whisper of something greater, a truth still waiting to be named. A truth that binds all things, seen and unseen, in the geometry of existence. There are moments in science when certainty begins to fracture, when numbers no longer agree and the universe itself seems to resist definition. In the early years of the 21st century, cosmology reached such a precipice. The deeper astronomers peered into the cosmos, the more the data began to diverge. The Hubble Space Telescope measured one rate for the universe's expansion. Observations from distant supernovae, those brilliant detonations of dying stars used as cosmic mile markers, suggested another. And yet the cosmic microwave background, the ancient light mapped by Planck, whispered a slower rhythm altogether. The universe was expanding. Of that there was no doubt. But how fast? The answers no longer matched. This growing contradiction became known as the Hubble tension. Each method was sound, built upon decades of refinement, yet each pointed to a different truth. It was as though the universe were speaking in two languages at once, one from its ancient past, and one from its living present. If the early universe and the modern cosmos truly expand at different rates, then something fundamental in physics may have changed. Perhaps the cosmic constant Einstein once inserted into his equations, the quiet energy of empty space, is not constant after all. Some proposed that dark energy itself may evolve with time, shifting as the universe ages, altering the tempo of cosmic expansion. Others suspected that our understanding of gravity, the most enduring pillar of physics, might be incomplete at the larger scales. The idea unsettled even the most seasoned cosmologists, for if the equations no longer align, it is not merely the measurements that are in conflict, it is the framework of reality itself. At the heart of these mysteries lies a far more delicate possibility, that the universe is not as stable as it appears. In quantum field theory, the vacuum of space is not truly empty. It seethes with activity, a restless sea of virtual particles that blink into and out of existence. Energy, fleeting and invisible, stirs the void. According to calculations, the Higgs field, the energy field that gives mass to particles, may not be settled in its lowest possible state. It could be a false vacuum, a fragile plateau of stability perched above a deeper abyss. If this is true, then our entire universe exists inside a temporary bubble of false stability, and like any bubble, it could burst. The physics of such a collapse are chilling in their precision. A quantum fluctuation, a random twitch in the energy of space, could trigger the transition to a true vacuum, where the Higgs field drops to its lowest energy level. The boundary between the old vacuum and the new would expand at nearly the speed of light, rewriting the laws of physics as it moved. Atoms would disintegrate. The constants that define matter and light would change. Every star, every structure, every trace of what once was would vanish, dissolved into a different reality. It would not be an explosion, but a quiet unmaking, a return to perfect, indifferent simplicity. Physicists call it vacuum decay, and though it remains a theoretical possibility, the numbers offer uneasy reassurance. The half-life of such instability may be longer than the age of the universe itself. Still, the idea lingers that the cosmos could be an echo balanced upon a metastable edge. For some scientists, the vacuum's instability is not a threat, but a clue. If space-time can exist in a false vacuum, then perhaps it is not a passive stage for matter and energy, but a dynamic participant in its own creation. Quantum fluctuations, ever shifting in the dark, might not merely disturb the vacuum, they might sustain it. The universe could be, in essence, a self-sustaining mirage, a delicate balance of opposing infinities, each preventing the other from collapse. This is the strange harmony of quantum field theory. The energy of the vacuum is not zero, it is vast, so vast that, when calculated, it should have torn the universe apart long ago. Yet gravity, through Einstein's equations, cancels much of that energy out. Somehow, the violent chaos of quantum mechanics and the smooth curvature of general relativity coexist, two opposing visions of reality in perfect mathematical tension. It is as though existence itself depends on the universe's refusal to reconcile its own contradictions. But the deeper scientists probe, the more fragile this balance appears. At the smallest scales, where quantum mechanics reigns, particles obey no fixed laws of position or motion. Probabilities replace certainties. At the largest scales, where gravity rules, space and time bend with predictable grace. These two domains, the quantum and the cosmic, describe the same universe, yet they speak in irreconcilable dialects. Attempts to unite them have birthed theories of unification: string theory, loop quantum gravity, holographic duality, frameworks that imagine space and time themselves as emergent, woven from deeper quantum relationships. If these ideas are true, then the fabric of the universe is not continuous, but granular, a web of information flickering in and out of being. Reality, then, is not built of particles or waves, but of relationships, of entanglements stretched across space-time. And within that entanglement may lie the reason why the vacuum does not collapse, why space-time does not dissolve, and why something exists instead of nothing. Yet even as theory strives toward unity, the data continues to defy expectation. Telescopes designed to study the early universe return measurements that diverge from predictions. Simulations of cosmic structure show subtle mismatches in the clustering of galaxies, the distribution of dark matter, the temperature fluctuations of the cosmic microwave. Background. Each new observation seems to whisper that the rules of physics may bend in ways we do not yet comprehend. Some researchers now speak of new physics, unknown forces or particles beyond the standard model, hidden symmetries that might restore coherence to a cosmos that seems to fray at the edges. Others take a more radical view that perhaps there is no single universe to explain. If inflation, the explosive expansion that followed the Big Bang, continues eternally in some regions of space-time, then there could exist countless universes, each with its own laws and constants. In such a multiverse, our own could simply be one of many bubbles in an infinite sea of possibility. The Hubble tension, the vacuum instability, the discord between quantum and gravity, all could be the signatures of a deeper structure we can barely glimpse, a reality not broken but layered. And so, modern cosmology finds itself in an uneasy equilibrium, a science defined by precision and paradox. The instruments that once promised clarity now reveal contradiction. The constants that once anchored the cosmos now drift, ever so slightly. With each new observation, it is as if physics has turned inward, confronting the limits of its own comprehension. The equations still work. They still predict orbits, particles, and the whisper of distant galaxies. Yet beneath their surface hums a growing uncertainty, a quiet recognition that even the most elegant theories may be provisional. In the mirror of the cosmos, science sees not just the universe, but its own fragility, its dependence on assumptions, its longing for coherence, its relentless drive to explain. The universe continues to expand, galaxies continue to recede, the cosmic clock ticks forward. And yet, beneath that steady rhythm, a question endures, one that no telescope, no particle collider, and no equation can yet answer. What if reality itself is temporary? What if the laws that define everything are not eternal, but evolving, shaped by deeper principles still unseen? The universe may not be breaking. It may be becoming, rewriting itself, one contradiction at a time, on the ever-shifting surface of existence. A cosmic story told by forces that cannot agree, yet somehow endure together, for now. In the aftermath of confusion, science turned inward, toward the invisible architecture that might lie beneath the known. If the universe refuses to collapse, if it remains whole amid contradiction, then perhaps its stability is not written in the visible forces of matter and light, but in something deeper, in the unseen mathematics beneath existence itself. Across laboratories and blackboards, physicists began to speak of hidden frameworks, vast, elegant geometries that might hold everything together. Some believed gravity was not a fundamental force at all, but an echo of something more profound, an emergent property, rising from the restless sea of quantum information. The old vision of gravity, a curve in the fabric of space-time, gave way to a new possibility, that space-time itself may not be fundamental, that it may be born from patterns of information, from the quantum connections that link one particle to another. In this view, the cosmos is not held by invisible strings of force, but by invisible relationships, the entanglement of everything with everything else. Entanglement, the most haunting concept of quantum theory. When two particles become entangled, their properties remain linked no matter how far apart they drift. Measure one, and the other responds instantly, as though space itself were irrelevant. Einstein called it spooky action at a distance, an insult to reason, a violation of common sense. Yet experiment after experiment confirmed it. The universe is woven together in ways that transcend space and time. If these connections are not limited by distance, then perhaps they are the foundation of space itself, a network of correlations, invisible yet absolute. From this idea emerged one of modern physics' most radical suggestions, that gravity itself might arise from the thermodynamics of information. In 2010, theoretical physicist Eric Verlinde proposed that gravity is not a force, but an entropic phenomenon, a byproduct of the way information is stored and distributed throughout the universe. In this framework, space-time bends because information seeks balance. Matter moves not because it is pulled, but because the universe, like a vast computation, adjusts its data toward equilibrium. Gravity, in this sense, is the echo of entropy, the universe's constant rearrangement of its own memory. At the intersection of this idea lies another, more audacious still. If space-time and gravity are emergent, born from the information-linking quantum states, then perhaps the entire universe is a projection, a hologram. This concept, once dismissed as speculative poetry, has found mathematical credibility through the work of Juan Maldacena and others, who showed that certain quantum systems, without gravity, can describe a universe with gravity in one fewer dimension. It is known as the ADS-CFT correspondence, but its implications stretch beyond the equations. It suggests that the three-dimensional universe may be the shadow of a deeper, two-dimensional reality. Every star, every galaxy, every human thought could be encoded on the cosmic boundary, projected inward like light from a film onto a screen. If true, then reality itself is a map of information. Every bit of energy, every quantum fluctuation, every gravitational curve is part of a grand holographic code. The universe, seen not as matter in motion, but as meaning in formation, and yet in all these visions, the same question lingers, the same haunting thread that runs through Newton's apple, Einstein's space-time, and the trembling uncertainty of quantum fields. Why does it hold? What keeps this code from corrupting, this information from dissolving into randomness? In the mathematics of string theory, another candidate for the architecture of all things, the universe is imagined not as point-like particles, but as vibrating filaments of energy, each note giving rise to a different property of matter. Gravity, electromagnetism, even time itself, all could be harmonics in a vast cosmic symphony. But the strings too require a stage, a higher dimensional space in which to vibrate, known as the bulk. And within that bulk, infinite possible universes could exist, each governed by slightly different notes of the same eternal music. It is a vision both elegant and unnerving, that the structure of reality could be the result of resonance, of mathematical song, of vibration without intention. Still, even string theory, for all its beauty, remains incomplete. It cannot yet be tested. Its predictions are hidden beyond the reach of our instruments. It offers not final truth, but a glimpse, a whisper of coherence in the chaos. Amid these grand architectures, physicists began to see a strange parallel between their equations and their own existence. The universe seeks structure, patterns that persist, symmetries that endure, constants that remain stable against decay, and so does the human mind. From the earliest myths to the most precise measurements, the same longing recurs, to find meaning in the invisible, to understand the order behind the apparent disorder. The equations that describe spacetime are not so different from the stories that describe human experience. Both are acts of connection, attempts to hold together what might otherwise drift apart. Perhaps that is what the universe is doing, too, not merely expanding, but remembering. Each atom, each photon, each ripple in the cosmic microwave background, a record of an earlier state, a memory encoded into the fabric of being. If space-time is information, then reality itself is a story told perfectly, without an author, without an audience, yet endlessly coherent. Some theorists take the idea further still. They imagine that the universe is a quantum computer, a self-calculating system where reality emerges from computation, from the ceaseless processing of possibilities. Every interaction, every collision, every photon exchange between particles is a line of code executed by the cosmos. Every cause and effect, every birth and decay, a computation resolved. In this view, existence is not continuous but discrete, not a flowing river, but a vast digital sea, each Planck length and Planck time a pixel in the simulation of being. Such ideas echo the ancient question of whether reality is fundamentally material or mathematical, whether the universe is, or whether it is merely described. If the holographic principle and quantum information theory are both true, then perhaps being and knowing are the same thing. The fabric of the universe woven not of matter, but of meaning itself. And yet amid the equations and the speculation, the same quiet unease remains. The universe could have been chaos, it could have been unstable, asymmetric, incoherent, but it isn't. From the smallest quantum to the largest galaxy, the same laws hold. At least, almost hold everywhere. The same constants, the same delicate ratios, the same hidden symmetries. Physicists call this fine-tuning, though the term suggests intention where there may be none, but still, the numbers are exacting. Change the strength of gravity, or the charge of the electron by a fraction of a percent, and stars would never form, atoms would never bind, time would have no direction. It is as though the universe has chosen, somehow, to remain possible. The search for the hidden architects of reality is not a hunt for gods or designers, but for principles, deeper laws that explain why the laws themselves exist. And yet, the more the equations evolve, the more the mystery seems to grow. Perhaps there are no final laws, only emergent patterns, endlessly self-organizing, forever rewriting themselves as the universe expands. In that sense, the cosmos may not be held by gravity or dark energy or even space-time, but by persistence itself, by the universe's own refusal to let go. Just as meaning survives within the human mind, carried through memory, language, and thought, the universe may carry its own form of coherence, a cosmic memory that refuses to fade. Every theory, from Einstein's curvature to string vibration, from holographic horizons to quantum entanglement, circles this same silent question: what stops the unraveling? Why does the void not reclaim what it birthed? The answers may never be final, for the universe may not be built to end in certainty. It may exist to endure in wonder, a vast, unfinished thought still holding itself together against the tide of nothingness. There is a silence that exists only beyond the atmosphere of worlds, a silence that does not end, but deepens. Out there, between the galaxies, lies the quiet scaffolding of existence. Stars drift like embers caught in an unseen wind. Whole clusters move as if tethered by invisible strings. And through that stillness, light continues its impossible journey. Ancient photons, older than the continents, older than memory itself. Each beam that touches an eye, a sensor, or a mirror carries with it the ghost of the beginning. A fragment of the first light that broke free when the universe cooled enough to let atoms breathe. That light, stretched and thinned across time, is a reminder that the cosmos, in all its magnitude, remains exquisitely balanced upon what cannot be seen. The question of what holds the universe together has driven centuries of thought, of mathematics, of quiet awe. It is a question that bridges science and philosophy, calculation and wonder. For when everything visible is stripped away, what remains are the forces that do not show themselves. The gravity that bends the paths of galaxies, the quantum fields that hum beneath matter, the subtle tensions that prevent reality from dissolving into chaos. Gravity pulls, entropy unravels. Expansion stretches every structure to its limit. And yet, against every tendency toward disorder, coherence persists. A planet holds its orbit, a molecule keeps its bond, a heartbeat continues. In the grand arithmetic of the cosmos, this persistence is improbable. The constants that define the strength of forces, gravity, electromagnetism, the nuclear bonds, are balanced with a precision that defies intuition. Were gravity slightly stronger, stars would burn too quickly, collapsing into black holes before life could ever emerge. Were it weaker, matter would never gather. Stars would never ignite. The cosmological constant, the quiet driver of expansion, too, is tuned within impossible margins. If it were only a fraction greater, galaxies would have torn apart before forming. If smaller, the universe might have collapsed back into itself before light could find its way. Every variable, every physical law, seems adjusted not by chance, but by an unknown harmony, a fine-tuned orchestra playing in the void. Scientists resist mysticism, yet even within equations there lingers a sense of reverence. The Standard Model, the laws of thermodynamics, general relativity, all describe a world that should not hold together as beautifully as it does. And still, it does. Some theorists suggest that this balance is not miraculous, but inevitable, the result of infinite trials. That somewhere, among countless possible universes, only the stable ones persist long enough to wonder at their own stability. Others find meaning not in multiplicity, but in fragility. The idea that rarity itself gives rise to value. Perhaps this universe is not perfect, but lucky. It is held together not by certainty, but by tension, by the constant negotiation between forces that pull and those that push, between gravity's embrace and dark energy's release. Like the surface of a bubble, the cosmos expands, but does not yet break. Quantum mechanics adds another layer to this delicate balance. Beneath the solid appearance of matter lies fluctuation, a storm of probabilities. Even the emptiest vacuum teems with virtual particles, appearing and vanishing faster than light could ever witness. These quantum tremors, imperceptible and relentless, may be what sustains reality's structure, the restless hum that keeps the universe awake. Some physicists speak of a quantum foam, a substrate where space-time itself flickers. Others imagine that every particle, every atom, is connected through a web of entanglement. That what happens in one corner of the cosmos whispers to another across incomprehensible distances. In such a vision, connection is not a metaphor, it is the architecture of being. And yet, even this connectedness is temporary. Every bond, from the molecular to the cosmic, will one day fade. Stars will exhaust their fuel. Galaxies will drift beyond one another's light. The universe will continue to expand into darkness, temperature falling toward absolute zero. The final horizon will come not with violence, but with silence, a perfect stillness where even photons run out of space to travel. It is in contemplating that distant end that the true wonder of the present becomes visible. For the fact that there is light, that there is structure, that there is awareness capable of observing them, all of this exists only because the forces of collapse and expansion, destruction and creation, remain for now in perfect balance. Every moment is therefore a miracle of coexistence between the gravitational pull that binds and the cosmic acceleration that separates. There exists a fleeting equilibrium, the narrow passage in which time flows, and in which consciousness, briefly, can look around and ask why. The philosopher and the physicist meet here at the same horizon. One searches for meaning in existence, the other for equations that describe its persistence. Both encounter the same mystery. That order arises from chaos. That symmetry breaks just enough to allow complexity, and that life emerges from conditions that border on impossibility. It may be that meaning itself is an emergent property, born from the same entanglement that gives rise to space-time, that to feel awe is to momentarily align with the structure of the cosmos itself, to sense, in some small way, the coherence that holds everything together. Even in the most distant galaxies, Even in the cold dust between stars, the laws remain. Gravity still binds. Light still travels. Time still moves. The universe still holds. And perhaps that is the quiet revelation that science, after all its searching, leaves us with. That existence does not need to be eternal to be profound, nor complete to be whole. The miracle is not that the cosmos will one day end, but that it exists now, suspended between infinities, long enough to be seen. As the final light crosses space, light that began its journey before Earth had oceans, before matter took form, it whispers the oldest truth, that everything is connected, even through nothing, and in that nothing, there is something immeasurable, the fragile miracle of being held. In the final quiet of the film, the camera drifts outward, past the rim of the Milky Way, beyond the filaments of the cosmic web, into the slow dark tide of expansion. There, at the edge of perception, the last light moves, faint, patient, undying. It travels through a silence older than creation, carrying the memory of every star, every collapse, every brief spark that ever was. That light is not a message nor a destination. It is continuity itself, the thread that weaves time into being. Even as the galaxies drift apart, even as space grows colder, the laws still whisper. The universe still holds. And somewhere, on a small blue world, awareness looks up, not to conquer, but to understand. For in the endless silence, in the measureless dark, there is still this. A moment of coherence, a breath of knowing, a universe briefly awake, and a single beam of light, crossing eternity held by nothing yet never falling apart.